Hello, grade 7. Welcome back to our online class. And finally, we're done with chapter 1 about sets. Now let's move on to chapter 2. It's about set of real numbers. In the previous chapter, the set of real numbers were already introduced to you. And some examples of real numbers are 2.1, the pi, 2, 1, 1/2. Any number that you know, those are examples of real numbers. In this video, we're going to talk about subsets of real numbers. So let's have this diagram. Let's study the subsets of real numbers through this diagram, starting with the set of natural numbers. The set of natural numbers are the counting numbers, and the counting numbers are the numbers that we use in counting 1, 2, 3, 4, 5, 6, and so on. Those are counting numbers. They are called natural numbers because it is natural for us to count starting at 1. Again, natural numbers are counting numbers. And these numbers are 1, 2, 3, 4, and so on. And in a set of counting numbers, or the set of counting numbers is divided also into different subsets, different sets. The first one is the set of prime numbers. When I say prime numbers, these are counting numbers whose factors are 1 and itself. Examples of prime numbers are 2, 3, 5, 7, and so on. 2 is the smallest prime number and the only prime number that is even, meaning to say the rest of the even numbers in the counting numbers, they are not prime numbers. They are called composite numbers. When we say composite numbers, these are counting numbers whose factors are 1 itself and some other numbers in the set of counting numbers. And there's one number here that is not prime nor composite, and that is 1. In the set of counting numbers or natural numbers, 1 is not prime nor composite. The rest of the numbers are either prime or composite. And if we're going to look at this diagram, this Venn diagram, the set of natural or counting numbers is under a bigger set called whole numbers. It means that all natural numbers here are whole numbers. In order to complete the set of whole numbers, we need to add the 0. So the set of whole numbers contains 0 plus the set of natural numbers. So we have 0, 1, 2, 3, 4, 5, 6, 7, and so on. Those are whole numbers. And the set of whole numbers is under a bigger set called integers. When negative numbers are already included in the set, then we're already talking here about integers. So integers are whole numbers plus the negative of natural numbers. That is, we have -3, -2, -1, and we have the 0, 1, 2, and so on. These are integers. Again, integers are whole numbers. These are the whole numbers plus the negative of the counting numbers. And the set of integers is under a bigger set called rational numbers. When you already include fractions in the set of in this set, then we already have the set of rational numbers. Rational numbers are integers plus the fractions. Okay, rational from the word ratio. It's a ratio of two integers. It's a ratio of two integers, or rational numbers are numbers that can be expressed in fraction form. So we can have here 1/2, -3/5. These are some examples of rational numbers, plus the integers, plus the whole numbers, plus the counting numbers. Based on this, I can say that natural numbers are rational numbers. Whole numbers are rational numbers. Integers are rational numbers. Integers are sometimes whole numbers. Integers are sometimes natural numbers. Okay? And there are numbers that are not rational. We call them as irrational numbers. Okay, the prefix ir means not rational numbers. These are numbers that cannot be expressed as a fraction form. Okay, these are non-repeating and non-terminating decimals. Examples of irrational numbers are square root of 2, pi. We have 1.2346 dot 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 dot. This is non-repeating and non-terminating decimal. So this is an irrational number. Pi is also an irrational number because this is the same as 3.14, 15, 9, and so on. Non-repeating and non-terminating decimal. If we're going to get the square root of 2, the answer is also a non-repeating and non-terminating decimal. Rational numbers the rational numbers can be repeating or terminating decimals. We can have 1.333 and so on. We also have 1.3, something like that. Actually, these two are just the same. The bar on top will indicate that this digit is being repeated. 1.3333 and so on. Okay? So rational numbers can never be irrational numbers. Irrational numbers can never be rational numbers. If we're going to look at the figure, the diagram closely, irrational numbers are completely different from this set here. Whole numbers can never be irrational numbers. Okay? When you combine the set of rational numbers and the set of irrational numbers, then we can have this bigger set, and this set is called the set of real numbers. All of these numbers are real numbers, and these are the subsets of real numbers. Irrational numbers are real numbers. Rational numbers are real numbers. Real numbers are sometimes irrational numbers. Real numbers are sometimes rational numbers. Take note of those statements because I'm going to ask you whether a statement is always, sometimes, or never true. And this diagram will help you determine, will help you answer that kind of question. Let's have some examples. In this table, P stands for prime, N stands for natural or the set of natural numbers, W the set of whole numbers, Z the set of integers. Why is it Z? You have to get use of the notation of the set used to denote the set of integers. It's from the German word Zahlen. So letter Z, set of integers. If you want letter I, it's still fine. Q stand or represents the set of rational numbers. It's from the word quotient, because when we talk about rational numbers, it's a ratio or it's a quotient of two integers. Q prime, it's the opposite of the set of rational numbers, right? Irrational numbers. And we have the set of real numbers. Take note of these notations. So if you have number 13, and I want you to determine what kind of number is number 13. Is 13 a prime number? If your answer is yes, then you have to check this box. 13 is a prime number because the only factors 13 has are 13 and 1, or 1 and itself. And since 13 is a prime number, it follows that it is also a natural number. It follows that it is also a whole number. It follows that it is also an integer. It follows that it is also a rational number. it follows that it is also a real number. Okay? Because prime numbers are always real numbers. Natural numbers are always rational numbers. Natural numbers are always rational numbers. Something like that. Let's have square root of 13. Square root of 13 is just like that. You can no longer simplify this. And square root of 13, when you convert or write that into decimal, it is non-repeating and non-terminating decimal, which means this is an example of an irrational number, and all irrational numbers are real numbers. It is impossible for a number to be classified as rational at the same time irrational. It's impossible. Next, let's have negative 2 over 13. Negative 2 over 13 is not a prime number because number one reason is this is not a natural number. This is not a counting number. It's not also a whole number because this is not whole. This is fraction. It's not also an integer because integer contains the set of whole numbers plus the negative of the counting numbers. What about rational? Is this a ratio of two integers? Yes, 2 and 13. 2 and 13 are integers, or we can have here negative 2 and 13. They are still integers. Therefore, this is check. And this is check. Negative 2 over 13 is a rational number. It's also a real number. Pi. This was my example a while ago under the set of irrational numbers. This is 3.1415 9 ... It is a non-repeating and non-terminating decimal. So this is an irrational number. This is also a real number. I'm going to add one more example. This time this is negative 7. Negative 7, this is not a prime number. This is not a counting number because we don't use negative numbers in counting. This is not also a whole number because a whole number is equal to the set of counting numbers plus 0. 0, 1, 2, 3, 4, 5, 6, and so on. This is an integer because negative 7 is the negative of 7. 7 is a counting number. And we get the negative of that, we have negative 7. That's integer. Okay? And if this is an integer, this is also a rational number because any integer can always be expressed as a fraction. Negative 7 is the same as negative 7 over 1. Actually, we can think of other fractions whose value is also negative 7, like negative 28 over 4. Negative 28 over 4, that's 7. Any number that you can express in fraction form, that's irrational, ratio, fraction, quotient. And this is also a real number. Okay, so these are the subsets of real numbers. Prime numbers. The other one is composite. It's not here. Set of natural numbers or counting numbers. They're called counting numbers because these are the numbers we use in counting. And it is natural for us to count starting 1. 1, 2, 3, 4, 5, and so on. W represents the set of whole numbers. Whole. 0 plus the counting numbers. Z, Zahlen, German word for integers, or you can use I. Okay? Integers, integral, integrity. Okay? Integrity, when we talk about your integrity, we're talking about your wholeness, something like that. That's why the set of integers consists of whole numbers plus the negative of counting numbers. Q rational numbers from the word quotient, ratio, fraction. Any number that can be expressed as a fraction, that's Q, rational number. Q prime, it's the complement of rational numbers, so irrational. And we have the set of real numbers. All of these numbers are real numbers. Okay? I hope that you learned something from this video, and see you in my next videos.